Okay, we're going to talk about Chapter 5, Applications of Derivatives. In this section, we're going to connect the derivative and the second derivative with the graph of f. How does this derivative tell us what the graph looks like as we go through? So, let me get my screen working here. What we'll learn about in this chapter is the first derivative test for a local extremina, concavity, points of inflection, second derivative test for a local extreme, and learning about functions from derivatives. Differential calculus is a powerful problem-solving tool precisely because of its usefulness in analyzing functions. First derivative test for a local extreme. Let's look at it. We have absolute min. If the derivative equals 0, it could be a min, could not be a min. We have a local max up here. Derivative equals 0. Derivative equals 0. That's local min. Derivative is undefined. It's a maximum. Derivative equals 0, no min, and local min. So we get a lot of different options to happen. It could be a minimum, could be a maximum, it could be nothing. And it could be where the derivative equals 0, or it could be undefined. That's what the first derivative test tells us. So the following test applies. At a critical point C, if the derivative changes signs from positive to negative at C, then f has a local maximum value. If the derivative changes sign from negative to positive, then it's a local minimum. And if f prime does not change sign at C, then f has no local extremes. At a left endpoint, if the derivative is less than 0 for x is greater than a, then f has a local maximum. At the right endpoint, if f prime is less than 0 for x is less than b, then f has a local minimum. These are a little harder to work with. Use the first derivative test to find local extreme values. Identify any absolute extreme. Okay, well, what do we have? No domain restrictions, so we're looking at the whole graph. So therefore, let's take the derivative of this. So we're going to start off by going up here and say, okay, let's take the derivative. So f prime of x is equal to 3x squared minus 27. We're going to divide by 3. Or factor out 3, I should say. Square minus 9, so my values are x equals 3 and a negative 3, where my derivative equals 0. So I'm going to put those on a number line. Negative 3 and 3. Now from here, what's happening to my derivative on this side? My derivative at a negative 4, I can plug in here, is 16 minus 9 is positive. If my derivative here is, let's say 0, is negative, and my derivative over here is going to be, oh, that's a big negative. This is negative, and this is going to be positive. So my derivative here goes from positive, sloping up, to negative, sloping down. So this is a maximum. Don't know which one. Then it's going to go slope down over here, and this one's going to slope down over here and go back up and continue back up forever. So one thing we notice here that these graphs keep on going forever, both directions. So these are neither one or any absolute. So let's look at what the book says there. Let's see what they say. Since it's differential for all x, only critical points are the zeros. We got that. Interval, the first derivative tells us the local max and local min, and there's no absolute max. So what we're saying is what we came up with. So this here, now I would write it out at x equals a negative 3. If I plug it back into my original equation, it would be negative 27 minus 80 plus 81 plus 3. So it would be what? 54 plus 3 is 57. This is a local max. Then over here at x equals 3, plug that in, I'm going to get 27 minus 81 plus 3 is 30, be negative 51. This is a local min because of what's happening with my sign changes as I go through the problem. They're going to give you lots of rules as we go through these. So for example, concavity and concavity down. If my derivative is decreasing, and my concavity will look like this. Concavity means it's concave down, looks like an upside down U. Concave up, upside regular U. If my derivative increases, it's upside down. It's a regular u. And there's more rules like that too as we go. The graph of a differentiable function y equals f of x is concave up on the interval I if the derivative is increasing on I. So if it's always increased, it's concave up. If the derivative is if it's concave down, if a graph of a differentiable function is concave down on an open interval I, then the derivative is decreasing on I. So if it's concave down, then the derivative is decreasing. If it's concave up, then the derivative is increasing. And I don't know if I agree with this rule. We'll talk more about this. I don't like using the concavity of the first derivative. I'd rather use the second derivative test. The graph, or not graph test, the concavity test. A graph of a twice differentiable function y equals f of x is concave up on an open interval where the derivative is greater than 0, and concave down on an open interval when the second derivative is less than 0. Okay, use the concavity test and test the concavity of this. So if I took my first derivative of this, so first derivative of this function is 2x, second derivative of this function is 2, and at this interval 2 to 8, well, it's always positive. So if I go back a screen, if on an open interval, the Greiss differential is concave up on an open interval if my second derivative is greater than 0. So my second derivative is always greater than 0 because it's always 2. So therefore this function is going to be concave up, which we know. X squared we know is concave up. Second derivative is always positive. A point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. It has a tangent line and point changes. So let's look here. Find the points of inflection of the graph of this function. And I'm just going to kind of walk through. There's a lot of writing here. So the first thing we have to do with points of inflection, let's go back to the definition again. Point where the graph of function has a tangent line and where the concavity changes. Now, so the point of inflection is the second derivative. So what we're going to do first is we're going to take the first derivative of this. Now it's a chain rule, 2e to this times the derivative of that. So if we do that, find the second derivative. First derivative is 2e to this times the derivative of the inside. It's this. Second derivative is now a product rule. So we're going to work out the product rule and we're going to get down to this as my second derivative. Now I'm going to wait for a second to have you copy that down. So we got this down now. Now one of the things is to find the points of inflection, we have to set them equal to 0. Well, the e function is never 0, so don't have to worry about that. This function, we had set it equal to 0. We add 1, divide by 2, take the square root. We're going to get plus or minus the square root of 2. Or plus or minus the square root of 1/2. These are going to be points of inflection. Now, what I would usually do to figure out points of inflection is a little bit more than this book does. I want to justify there's points of inflection here. Points of inflection is I'm going to take these points. You got a negative square root of 2 over 2. And we get a positive square root of 2 over 2. Now when I say square root of 2 over 2, that's the same thing as this. Now I'm looking at my second derivative. We know that this is always positive, so I don't have to worry about that part, but I do have to worry about this one. Now if I plug in 0 in here, I'm going to get a negative number. Right in here. Now if I plug in 2, negative 2, I'm going to get a positive number here, and plug in 2, I'm going to get a positive number there. Notice this second derivative changes from positive to negative, negative to positive. Now therefore, since it changes, this and this are both points of inflection, and we can plug them back into the original equation to get our points. So here's our x-coordinate, which is the same as this point. And then we took these values and plugged them into the original equation to get the y-coordinates. That's how you find points of inflection. Now, second derivative test, it says this. If the derivative equals 0 and the second derivative is less than 0, then f has a local maximum at x equals c. If f prime of c is equal to 0 and f double prime of c is greater than 0, then f has a local minimum at x equals c. So we got minimum and maximums here. So the first one says if the derivative equals 0, so we know it has a tangent line equals 0 there, and the second derivative is less than 0, second derivative is negative, then it's a local maximum. Find the extreme values of this. Okay, let's take the first derivative. We're on this graph. We're going to take the first derivative of this, and we're going to get 3x squared minus 6. Factor out of 3, we're going to get x squared minus 2. So x is equal to plus or minus the square root of 2. So there's our two critical points. Now what this rule says, if I could graph it out, and let's just check it. Here's a negative square root of 2, here's a positive square root of 2. Now I'm going to plug it in here. If I plug in negative 2 here, I'm going to get 4, 12. That's going to be a positive. If I plug in 0 here, I'm going to get a negative. And if I plug in 2 here, I'm going to get a positive. So we know that this is going from positive to negative. This is a local max. And from here to here, this is going to be a local min. Now, what we also can do is take the second derivative of this. Now, if I took the second derivative of this, we're going to get 6x. Now, if I plug in negative square root of 2, I'm going to get a negative value. If it's a negative value, the rule says, then it's a local max. Still follows the rule. If I plug in a positive square root of 2, it's going to be a positive value. And a positive value says it's a local min. That's what the second derivative test says. So let's go back to it. It says if I have a 0, I plug it in, and I get a positive value, it's a local min. If I get a negative value, it's a local max. Now just learning from derivatives, a couple things. If it's differentiable, it's smooth, connected, graph may rise or fall. If the derivative is greater than 0, the graph is going to rise to the left and right, maybe wavy. If it's less than 0, graph falls. If the second derivative is greater than 0, it is concave up. Throughout, no ways, graphs. If the second derivative is less than 0, concave down. The inflection point is where it changes signs from concavity. If y prime changes sign, the graph has a local max or min. If y prime equals 0 and y double prime is less than 0 at a point, the graph has a local max, and vice versa with local min. We're going to practice a lot of problems from these sections to get you used to these sections here, because there's a lot of different rules here. So that finishes off 5.1 through 5.3. Thank you.